So we already know that if you have an observable, which I've written here in its spectral decomposition, so these are the eigenstates of the observable and these are the eigenvalues, and you have a general state, which can always be written as a superposition of those eigenstates, then we know that if we take the average of a bunch of measurements, we can calculate that from the measurement postulate. So each time we make a measurement, we're going to get the result n, and the number lambda n and the state n with probability mod bn squared. So if we take the average of that, with this probability, we'll get this result. So this is the average result we'll get when we measure this observable. This can be extracted directly from the inner product. So if we expand the operator and the state here, and note that I cleverly chose a different dummy index in each expansion. Then all the sums come out. The two complex numbers come straight out. Then I've got the inner product between j and k, which is going to give me a delta function. I'm going to get the inner product between k and n, which is going to give me a delta function. And I've got my lambda k. So I can sum over the k and the n, and they'll both give me j. And so you'll see that this expectation value of the operator is exactly the average that we'll get if we measure that thing. And so that's how you calculate the average. Now, averages are going to change over time because the state is going to change over time. And the state's changing over time in a way that we know exactly. So if we have the state at some original time, then you can expand the state at a later time as just the time evolution operator times the state. And of course, if we know the expectation values tell us the average of any observable we like, which means they also tell us the average of the square of any observable, or the cube, or any power of any observable. And therefore, you can get the full statistics of any measurement you might care to make out of expectation values. So any theory that gives us all the expectation values is telling us everything we can possibly know about experiments. And you'll note from here that while the quantum mechanics we're used to kind of groups this time evolution operator with the states and assumes that it's the states that are changing, in fact, it's quite possible that you could decide instead to write a different theory that decided that all the operators were changing and group these evolution operators with the operators themselves. And it turns out that quantum mechanics was actually developed at the same time in these two different directions, and one of them is called the Schrödinger picture, and the other is called the Heisenberg picture. But you can see from this formula here that they're completely equivalent ways of formulating quantum mechanics. They give you the same predictions for every possible experiment.